Thanks to the conference for rescheduling me. I had a bit of a travel difficulty. Thanks for being here. My name is Zachary Kranz. I'm an undergraduate researcher at the University of Dayton in Dayton, Ohio, in the Department of Engineering Management Systems and Technology under Dr. Alex Watson. Today, I'd like to talk about a novel technique for strain-isolated interfaces between soft and rigid electronics. So soft electronics will become and are becoming extremely common and extremely useful tools to creating solutions for the future. There are many ways to create soft electronics. Inductors, capacitors, and resistors are all essentially technologies and topologies that have been worked out and are extremely useful. Semiconductors are coming a long way, have been coming a long way very recently, but we've seen quite a few presentations on this. So I think in the interest of time, I'm going to skip past this. So flexible hybrid electronics are the current standard for the industry for hybrid architectures. These consist of Kapton or polyamide substrate, material commonly used in the electronic industry, and have a conductive layer of copper or silver ink pattern to make traces. And these flexible hybrid electronics are commercially available in industry. So, however, the silicon semiconductors, while they can be thinned down to bend on a flexible substrate, when transitioning to a stretchable substrate, this causes some difficulties. Because of that, it is desirable to connect hybrid electronics to soft electronics. So in order to create truly soft electronics, it's necessary for a conductor to be used that is compatible with unique constraints of soft substrates. When patterned into traces, the resistance of the conductor must be low enough that significant amounts of power or signal are not dissipated as heat, and the resistance cannot change substantially as the substrate changes shape or stretches. For this reason, the group that I'm a part of settled on using polymerized liquid metal networks as our conductor of choice. This can be seen in the graphic. When it is strained, there is very, very little change in resistance with an R over R naught of not exceeding 1.85. Normalized resistance up to 700% strain. So this is a very, very strain tolerant conductor. These polymerized metal networks work very well for the specific application because of their structure and makeup. They are composed of a eutectic blend of gallium and indium, which has a melting point below that of ambient room temperature, and is separated into nanoparticles by means of a probe sonicator. These nanoparticles are then functionalized by means of a ligand shell and are suspended in a carrier fluid, which allows them to be patterned onto various substrates. We particularly use thermoplastic polyurethane, or TPU, in our lab. And once the carrier fluid evaporates, the particles that are left behind are then cross-linked into a film. Strength is then applied to the nanoparticles, which ruptures the ligand shells, and the liquid metal spills out and is able to be conducted electricity. This material can then be used to produce many types of soft electronics. So directly connecting a soft substrate to a hard one, such as TPU to traditional FR4 circuit board materials, can cause many issues. First of all, there's a massive change in the Young's modulus going from the hard substrate to the soft substrate. And that means when the sample is strained, the most likely failure point is actually at the junction between hard and soft. This intermediary or interface between these two materials causes issues. So in order to alleviate that, we can take another material that has a Young's modulus in between our soft and our hard materials and place it in between. We've been using Kapton in our lab, Kapton or polyamide film. And this provides some way to bridge the gap between hard and soft materials. However, this isn't a magic bullet. There are, again, some issues going from soft TPU to Kapton. There is a large difference in the modulus elasticity between Kapton and TPU. TPU has a modulus elasticity of around 3 megapascals, where Kapton has a modulus elasticity of around 3 gigapascals. the fact that you're going 3 orders of magnitude within a small area, 3 orders of magnitude of the modulus elasticity within a small area means that you can basically change the amount of stretch that a ink is going through under a very small amount of area. And this causes, in extreme cases, fracturing and cracking of our polyLMN liquid metal network. When the liquid metal network cracks, it causes discontinuity and failure of the sample. So in order to reduce that, we can further spread out the length of the modulus of elasticity change at the boundary layer between Kapton and TPU by manipulating the geometry of that boundary. Adding a concave section of the boundary will constrain a section of the TPU that is trapped in that section and allow a strain gradient to form. This keeps the conductive material from cracking when it's stretched. So we can see right at that, right at the interface of the Kapton and TPU, we've carved out a section of Kapton, and that allows us to set up a strain gradient. So our construction process is to first manufacture the samples. We use a vinyl cutter to cut a mask out of adhesive-backed vinyl in the shape of the traces that we want to pattern onto our TPU sample. This mask is then transferred to a piece of TPU, and conductive material is applied to the mask with the razor blade or blade coating method. It's used to flood the entire void in the mask and level the surface. The mask is then removed, and the conductive material is strained to activate it, rupturing those nanoparticles of liquid metal, allowing the liquid metal to spill out and percolate through our network. The mask is removed, and then we we place the interconnects onto our top encapsulation, place any electronic components that are going to be in the sample, and then press it in a heat press. Heated press at a pressure of 0.4 megapascals, temperature of 160 degrees Celsius for 120 seconds. Once this is finished, the sample is complete and ready for testing. So we took a look at our sample strain testing. We took a sample, we placed it into strain jig, and stretched it progressively higher and higher, and measured the resistance with response to stress. For an unstrain isolated sample, we were able to get up to 70% strain before the sample failed. Whereas when we got the strain isolated sample, we were able to continue, had continuity up to 200% strain, at which point the sample ripped in half. We did not have a loss of continuity on the strain isolated sample before the sample physically failed. So in order to more accurately figure out what was going on in our boundary, we did optical strain sensing. We took a pattern of ink dots and placed them on top of our sample, and then used an optical method to track the dots as they were strained under tension, and set up several different areas that were in our sample. So we tracked the movement on the polyamide on an area that was between polyamide and TPU, an area that was only in the TPU isolating region, an area that we called the border region, and then our unconstrained TPU sample. So plotting those on a graph, we have a gradient of stretch, essentially, from left to right on the sample, which allows us to keep our traces from disconnecting under high strain. And conclusions, strain isolation geometries allow for a strain gradient across critical electrical interface, reducing discontinuities and increasing the range of strain that polymerized liquid metal traces are useful. Thank you.